So here we go. We're going to do 6.3. 6.3, we're going to do sampling distributions and estimator. So we're doing sampling distributions, all right? So far, what kind of distributions do we know? We talked about, did we talk about binomial yet?
I forgot what it equals.
You forgot?
That was like the...
Did we do bins? Remember doing bins? Bins we did, right? Binary, independent, number of trials, same probability, right? Bins. So we did binomial, okay, we did binomial. And then we talked about the standard normal distribution, we talked about the normal distribution, right? Okay. So now we're talking about what's called a sampling distribution. A sampling distribution is where you have a population, right? You have a population and you're going to take a simple random sample. And you take, so if I have, let's say a proportion here with a standard deviation, I take the sample. So then I get a statistic, which is called the P hat, and then I can find also a sampling distribution, the standard deviation of the samples, all right? So every time I do a sample, what I'm going to end up doing is I'm going to go ahead and record a P hat, all right? So this is one of my first sample. And then I do completely reshuffle the deck, and then I do another sample. I find out what that P hat is, the sampling proportion, right? And do this, right? And I can go ahead and start stacking these up, right? And this would be a what? So this would be a distribution of the samples, right? Each sampling proportion, right, would be the distribution of that. It is a sampling distribution, okay? And we can do this not only for proportions, we can also do this for means, right? Means, right? Do a different color. So for a mean, I would have this and this. And over here I would have a sample mean, right? And then I would have a standard deviation of that sample mean. Okay? All right. So again, these are the parameters. We talked about this, right? Parameters. These are the statistics, right? Population, parameter, sample, statistic. P and P, S and S, right? Easy to kind of remember, right? Okay, all right. Okay, so that's that. So let's go to look at page 255. On page 255, we have, again, the proportions. It means we have not talked about the variances. Well, we did. I guess we have talked about the variances here, right? So, proportions. You take a sample, sampling procedure. So this is the top portion there, right? And you find each time, for each sample, you're going to find a sample proportion. You just stack those together right here, right? You stack them up to find the distribution of the samples. Same thing with the means, okay? And also with the variances, we'll talk about the variances later. Okay, flip the page. Go to page 256, definition, the first orange box. Anna, go ahead and read that for us.
The sampling distribution of a statistic, such as a sample proportion or sample mean, is the distribution of all values of the statistic when possible samples of the same size n are taken from the same population. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a probability histogram, formula, or table.
Okay, all right, good, good. All right, everybody understand that? Are we good with that? Should be good with that, right? Then there's a definition underneath that, the sampling distribution of the sample proportion. Okay, so this is the first one. We're talking about the first one, right? Okay, it's the distribution of sample proportions. with all samples having the same sample size n taken from the sample population, okay? So again, all samples will be taken with the same number of samples here, okay? You can't change this and put them together here, right? In other words, if I had a population of 10,000 and I'm taking a simple random sample of 100, you can't all of a sudden start taking random samples of 50 and include it into this, okay? They all have to have the same sample size, okay? Okay, we're good with that, all right? So underneath there, notation for proportions. P is the population proportion, P right here. P hat is the sample proportion, which is over here. Okay, behavior of the sample proportions. The distribution of sample proportions tends to approximate a normal distribution, voila. Okay, so we go from, I don't know what's here, but when I take the distribution sample proportions, they tend to be normal distribution, okay, all right. Number 2, sample proportions target the value of the population proportion in the sense that the mean of all of the sample proportions P hat is equal to the population P. So in other words, these two here are the same. Okay? So you read that, right? Which tends to be the same thing with the means. These two things will be the same. Okay? All right. Okay, and if you go to page, page 261, let's quickly go to page 261. There's a definition there. I'm skipping ahead a little bit, but this is kind of an important thing, so I want to nail this down right now. An estimator is a statistic used to infer or estimate the value of the population parameter. Okay? In other words, this is an estimator for this, or this is an estimator for this, same as this being an estimator for this and this for this. Okay? If you read underneath there, it says, an unbiased estimator is a statistic that targets the population parameter in the sense that if the statistic has a mean that is equal to the population parameter. So I already said that this is going to be the same as this, and then we call that an unbiased estimator. So I am using this to estimate this, but because they're the same value, there is no bias or no correction that I have to make to this to estimate this. That's why it's called an unbiased estimator. Okay? Same thing for this. This is an unbiased estimator for this. Okay? All right. And we will find out later that this is a estimator for this, but it is not an unbiased estimator. You have to make corrections to this guy to say to use this. Okay, you have to multiply, divide, or something, or do what? Something has to happen to it. Okay? All right, go back. Let's go back. So we're back to page 257, example number 1. Example number 1. Consider, where are we at? Consider repeating this process. Roll the dice 5 times. Find the proportion of odd numbers, 1, 3, or 5. Okay. What do we know about the behavior of all sample proportions that are generated in this process as this process continues indefinitely? So if you look at the underneath there, it shows you what we're doing. So we're doing 5, right? So what are the possible values that we can get here? What are the possible values? How many can we get? How many odd numbers can we get?
3.
We can get 3. Is that the only one? Okay. how many of these can we get, right? We're rolling it 5 times.
All 5.
All 5 of them could be odd. All 5 of them could be even, right? So the only probability or possibilities that I have are 0, 1, 2, 3, 4, and 5, correct? I'm not getting anything else, right? So I can get 0, 1, 2, 3, 4, and 5, okay? These are not odd numbers. These are the number of odd numbers you're getting each 5 times that you roll it, right? Okay. And if you look at on that same diagram on the very end, on the red, there is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's why the histogram has 6 separate bars there. You see that?
Yeah.
Right? It's going from 0, 0.2, 0.4, 0.6, 0.8, and 1, right? Right? Okay. Because if you got 3 out of 5, the proportion is what? 3 out of 5, which is 0.6, correct? Right? 4 out of 5 would be 0.8, 1.0, so on and so forth. So what is the mean of the sample distribution? Okay, what does that sampling distribution look like anyway, to begin with? The red histogram. Does it look normal to you? Looks pretty normal to me, right? It looks fairly symmetrical, right? And it's bell-shaped, right? Okay, so I would call it a normal distribution, right? With a mean of what? What's in the middle? I know it's really small, but you can read there. Is it 0.5? Can we agree that it's 0.5, right?
I'm gonna say 0.45.
Well, no, because the other one's 0.6, right? So you're in between 0.4 and 0.6, so it must be 0.5. Okay, all right. Sampling distribution of the mean. Now we'll go look at the mean. Okay. So let's go ahead and flip the page. Well, okay, let's go ahead and read the definition first. On page 257, Spencer, go ahead and read that for us.
The sampling distribution of the sample mean is the distribution of all possible sample means, or the distribution of the variable
X bar, okay.
With all samples having the sample size n taken from the same population, the sampling distribution of the sample mean is typically represented as a probability distribution in the format of a probability histogram formula or table.
Okay, sounds very similar to the one we just read for proportions, correct? All we're doing is just changing the proportions to a mean now, okay? All right, so now we're doing the blue ones here, right? We have a mu here, and we'll get a X bar, sample mean, right? Okay, and these are the same, right? These are the same, because it's in what? What is this called?
What's what called?
These two are the same, right? Just as these two were the same, numerically, right? They were the same value. These two are the same also. We called that what? An unbiased estimator, right? It's unbiased estimator. Okay. All right. Okay, flip the page. Let's go to example number 2. Oh, this is very long. Eliana, go ahead and read that for us.
A friend of the author has 3 children ages 4, 5, and 9. Let's consider the population consisting of 4, 5, and 9. We don't usually know all the values in a population, and we don't usually work with such small population, but it works both in principle. If 2 ages are randomly selected with replacement from the population, identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. Do the values of the sample mean target the value of population mean?
Okay, all right, good, thanks. So we have 4, 5, and 9. This is my population. I have 4, 5, and 9, right? And I am taking a sample of how many? How many am I sampling? Huh?
Two.
Two, right? Two, right? Okay. So, what are the possibilities? The first one, I can get a 4, and the second one, 4. This is one possibility. 4, 5, 4, 9, 5, 4, 5, 5, 5, 9, 9, 4, 9, 5, 9, 9. Can you see that as the 9 distinct possibilities, right?
Yeah.
Because I have 3, I can be 3 out of any out of these 3 of the first, and then any 3 on the back, right? So that's why can you see the logic of how I group these? 4s, 5s, and 9s, and then 4, 5, 9, 4, 5, 9, 4, 5, 9, right?
Yes.
So the possibility of me getting this is what?
1 9.
1/9, right? Because that's 1/3 times 1/3, right? As a matter of fact, it should be the same all the way through, right? So
Yes.
1/9. These are the probabilities of me getting this selection. Okay. What is the mean of this? I would have to add the 2 and then divide it by 2, correct? 4 plus 4 is 8, divided by 2 is 4. What is the mean here? So this is the sample mean. What is the mean here?
4.5.
4.5,
6.5.
6.5,
4.5.
4.5,
5.
5,
6.5.
6.5,
7.
7, 9. Correct? Okay. So what are the possible values that I can get here? I can get 4, 4.5, 5, 6.5,
7.
7, and 9. Right? So what is the probability when you're getting 4?
1 9.
There's only 1, right? What's here?
2 9.
I have 1 here and 1 here. Okay, we already checked that one off. 2 9s, 5,
1.
1, 6.5,
2.
2 of them, right? 2, 7,
2.
2 of them. 9, 1 9. Okay. So to find the mean of that, I would just multiply these across and then add them together. Okay? So I do that, I get 4 9s. This is what? 9 9ths, right? Because if I'm multiplying it 9, right? And then I get 5 9ths. I get 13 9ths. 14 9, right? So if I add these all together, the tops, I'm going to get 4 plus 9 is 13, 18, 23, right? I'm just trying to add these together without using my calculator. So I add these two, I get 31, 54,
Yes.
which is,
6.
so this is my sample mean, right? The mean, this is the X total of all of them, right? What is my population mean? It's just the mean of these 3 numbers, right? Which is what? 6. So what do we prove? We prove that it's an unbiased estimator, correct? Right? You can see that this is the same as this. So it actually does work. Does that make sense?
So you can just do that.
Yeah, we can just use this one. So this is it. We know it's going to be this, right? Okay. All right. I will leave example number 3 for you guys to do on your own. It's just reading. So on this one, we're doing the same thing, okay? Well, actually, kind of the same thing, okay? But on this one, we repeat the process 10,000 times, which we are not going to do, okay? So I'll let you guys read that through, see if that makes sense to you. And we will call it a day. And actually, I'm not going to issue any homework today.
No. No.
I know. Well, what happened, right? What happened?
Unless you're hard.